So generative AI is having a moment. And so why is it having a moment? Well, suddenly the public has access to ChatGPT and Bard and other chat bots, and they have image generators, Midjourney, DALL-E, Stable Diffusion, that are producing these very convincing outputs of text and images. Now, there were predecessor versions of these technologies, but what's happened is in recent days, they have gotten much better at what they do. So part of what we have to understand is, why did that happen? If you've used a language translation tool, if you talk to a smart speaker, if you chatted with an e-commerce virtual agent, you've used generative AI. So it's not like there's some Kuhnian paradigm shift that's happened in the science. It's just that when OpenAI released ChatGPT version 3.5, which suddenly was able to produce very convincing seeming text, and it seemed to know a lot, everybody had a pretty big reaction. And this was true even in the tech community, even in the participants in the tech race that's going on. And we'll talk a little bit about what was surprising even to the technologists. But lots of people had reactions. Some people overreacted, okay? No, ChatGPT and these, they're not alive. And this, what is so-called artificial general intelligence, which would be a machine that truly can think like a human, that's not what this is. But nonetheless, the stakes are high. This technology is demonstrating increased capacity and capabilities on a daily basis. How long is it going to be before generative AI is connected to 3D printers and then the technology is actually going to be producing objects in the world? That's going to happen. So people in the general public have basic questions. What is this? Where did it come from? How does it work? And our answer is, it's not new, but it's better. And we'll talk a little bit about why. From the computer science perspective, in 2015, a new way of dealing with image generation that sort of goes from an all or nothing method to a bit-by-bit method actually produces much more convincing images. In 2017, a way of reading your text prompt to read it as a whole and assess the relevance of every part of your prompt is part of why you're getting so much more personalized responses from the chatbot. And the other big thing is scale. And scale is the big takeaway. What's happened is the computing power and the amount of data, when you scale it up to a certain level, you start to see a sort of step level increase in the value of what you're getting. Now, for copyright lawyers, the main questions that we want to know about is, okay, well, at least for the creative sector, where do these works of authorship, how do they get used in this so-called training? How are they used when the machine is actually doing its thing? And are these infringement machines? Is that what their purpose is? Because sometimes they appear to put out infringing outputs. What's going on? So just quick observations. Generative AI is affecting all kinds of areas of law. Copyright is sort of at maybe the tip of the spear, but there are other areas of law that will have a say about how we regulate this technology. And within this creative sector, generative AI is really just one of the automated tools, especially in the music sector. There are older versions of, The Weeknd and Drake mashup. That was using an older form of AI. It wasn't using this stuff. So you can create convincing fake music without needing to use this. And in fact, OpenAI's sort of research on the music side is in a much earlier stage. And right now its outputs are pretty unconvincing or not nearly at the same stage that text and images are, but that will change. Some basic design. So we're going to use these words model or system. And what are you talking about? And since, at least for the fair use analysis, the purpose of using copyrighted works is a legally relevant question, then at least it's useful to talk to the computer designers and say, in your version at least, what do you think the purpose is of what you're trying to do? And the goal is to create prediction engines. And this is really the important thing to understand. These machines, these systems don't know anything. They are not a library. They are not a search engine. They are designed to predict what you want based on your output. And this prediction technology is not that new. So Charles, classifiers are the older version. Tell us a little bit about sort of older uses of classifiers.
So the idea of having a data set and trying to solve this problem of, some of the pictures are cats and some of them are dogs, or, these images are the digit 1, these images are the digit 2, these images are the digit 3. That's a very old problem. People have been trying to tackle this since really the beginning of computing. And so there have been a number of different approaches. The usual way is just sort of straightforward rule-based approaches. I look for certain features that I've hard-coded into the program. The sort of modern scope of AI uses what are called artificial neural networks, and they use essentially a set of mathematical calculations that are learned to do that sort of classification. But ultimately, all it's doing is it's taking a set of inputs, basically a list of numbers, and it's trying to transform that into another list of numbers. That list of numbers indicating this is a cat, this is a dog. So we're going to show kind of how that works. But that's ultimately the goal of these sorts of things. And you can imagine how these sorts of classifiers are used in all sorts of daily life. I have an exercise app actually that if you input like the 3 types of exercise you're doing, it'll try to guess which muscle group you're exercising. That's a simple classifier, and they actually trained that using the techniques we're about to talk about.
And this is actually the earlier version of how you would train an image generation generative AI, is you'd ask it to be able to, you'd have one system that's putting out half fake, half real images, and the other system has to guess which is which. And so you'd ask the classifier, so what do you think, real or fake? Fake, right? Now, how did AI do this? So it's also doing predictions. The classifier is just predicting yes, no. Now we're predicting a much wider set of variables, but it's still fundamentally a prediction engine. How did it do it? It was trained to learn the patterns of catness in terms of a set of statistical values that are associated with the image of a cat, the jawline, the eye line, and all of that. And then it uses those statistical associations to say, in response to a prompt, give me a cute little kitten with big eyes, the left image, voila. They're using a technical architecture and a computational model called connected neural networks, right? Now, this is another big important point. If you talk to ChatGPT or Bard and you get these sophisticated sounding answers, then what must be going on is brilliant mathematics, right? If they're able to handle these complex tasks, then there must be an Einstein in the box. No, you don't want an Einstein in the box from a computational perspective. Why? If I had to write a model that had that many different steps in its computation, why would that not be the way to solve these problems?
The main thing is it would be really hard to write that program. Somebody would basically have to imbue all their thoughts into hard-coded lines of program. And what we want is something that we can just say, here are a bunch of examples. Can you figure out some patterns out of them? Simple math allows us to do this in the same way that statistics allows us to draw nice linear regressions among data.
Yeah, so that was the early version of language translation. When we didn't have a lot of computing power, let's try to teach the model the rules of grammar. Guess what? Think about all the exceptions in any language, and then think about how that computer program would have to. It doesn't work. It tried, it didn't work. Instead, break the task down and don't ask the machine to know anything, right? So here's your other big takeaway. If you take nothing else from this, when the next time you interact with Midjourney or ChatGPT or Bard, you are essentially talking to a network of 4th graders who each has been assigned a simple math problem. It's the number of 4th graders inside these machines that is what is doing the power. You need a little calculus and linear algebra to train it, but once it's trained, the engine is 4th grade math. And you need billions of 4th graders. That's essentially what's happened in this field. So it's all about the huge scale. It's the scale of the computational data. It's the scale of the power that is making all of these calculations. So it's not Einstein math. It's college math to train, and then 4th grade math to operate is basically what these models are doing. And if we go back to the network, the first thing we have to do is train the data. So from the copyright perspective, now your ears should prick up. Okay, so we're going to take a lot of text and a lot of images. Those are already in digital format, but are they useful for training in the sort of zeros and ones? If I pull it all off the web, am I ready to train?
Well, so the first thing you have to do is you have to decide what is the architecture of the system that you're going to be training on. So somebody has to go in there and they design sort of this network. They say, we're going to have this many fourth graders here and this many fourth graders in this classroom, this many fourth graders in this classroom. These are what we're going to call the hyperparameters of our model. They're going to basically lay out what our model is going to look like, but it doesn't actually have any information in it yet. It can't do anything useful. So we start off by essentially assigning all of our fourth graders random tasks. Multiply this number by 3, multiply this number by 7, multiply this number by 2. They will, by performing these calculations, produce an answer to your task. So I give them an image and I say, like, is this a cat or a dog? And they'll say cat, but is that right? Probably not, because I just assigned them random numbers to work with. Those answers are probably wrong, but we can also see how wrong they are by comparing them against the ground truth. The question then becomes, how do we update the information the students have? How do we change the cards that they're holding so that they produce a slightly better answer, right? And if any of you are familiar with calculus, this is simply a matter of taking derivatives, right? We're just trying to figure out if we change their answer slightly one way, can we get them to give more correct answers? Again, this is over the entire training set, not over a single one.
So this is the first stage. Is it a cat or is it not? It doesn't know anything, but it's not a cookie monster. It is not ingesting the copyrighted data. Instead, the copyrighted data is being shown to the model in the same way that you would be looking at it, but you're not actually taking a copy home. You're not putting it on your shelf. You're looking at it, analyzing it at a distance and saying, what can I learn to change the math inside my parameters?
Okay, so our training process kind of looks like the following. So we've got this set of images. Some of them are cats, some of them are dogs. We then pass it to our army of fourth graders. We ask them, hey, evaluate all of these images, okay? They perform the math. They produce a list of answers. And you can see that list of answers over on the right side. They said the first one's a cat, the second one's not, the third one's not, and so on. Okay. Like I said, at the start, the fourth graders are just given random information. They're given random numbers to work with. Those answers are almost certainly completely useless, right? So how do we improve them? Well, first we grade the class. We say this one was right, this one was not. But then we have to go and we ask, which of the students caused the most problems over the training set? So first student, if you increased your number, we would have gotten like a 2% increase. So you raise your number a little bit. Second student, if you drop your calculation by 5%, we would have improved our results. Again, we're looking over the entire training set, not a single input, because we want to improve the results over as many things as possible. Based on this, we can say, okay, we want to update what each of our fourth grade students is doing. We repeat this process many, many times, making small increments, right? And at the end of it, just by virtue of doing this so many times with so many fourth graders, we eventually come to a set of numbers that we're going to call the parameters of our model that will actually do a pretty good job of figuring out which things are cats and which things are dogs. And that's really the magic of this whole thing. By just repeating small, simple calculations, we're able to actually make these sorts of determinations with surprising accuracy. You can actually mathematically prove that a network with enough fourth graders in it will be able to calculate any mathematical function or any performable computation with actually just 2 classrooms. You just have to have a large enough number of fourth graders in each classroom.
Images are fun, but like the fact that you can ask it to write a summary judgment brief, and it actually will. So let's say we get an output that's the equivalent of 5 pages of a legal brief. What were the prediction steps that led to that output?
What our army of fourth graders are really doing is they're making small predictions, and then we're aggregating those predictions together that produce some sort of coherent whole. You start with a list of numbers as inputs. So when you're talking about like words that go into ChatGPT, or we're talking about graphics that go into an image classifier, the first thing we have to do is break them into numbers. And there are lots of ways of doing this. Computer scientists have a number of like really well-defined ways. They're called like embedding vectors, various things. We then provide this list of numbers to our army of fourth graders. And the reason that fourth graders make sense is that they tend to sit in nice little rows. You pass the numbers down, and each fourth grader is just holding a card saying, multiply by this, You see, the first one multiplies by 5. So that person is going to multiply 17 by 5. The person below that student is going to multiply by 0. Sometimes you don't care about the number. You multiply 17 by 0, you get 0. They're going to just do multiplication straight down the line. There's a row monitor over at the end. They're going to go and collect all the numbers in the row, add them up. So the numbers that the kids in the array are doing, those are called the weights. The numbers over there that the row monitors add, that's called the bias. So far, all we've done are simple multiplications and additions. We then do this thing called an activation function. This is just a sort of nonlinear transformation. The most common one is if it's a negative number, make it 0. Not terribly hard to do. This produces another list of numbers. We can take that list of numbers and possibly interpret it as a word that's going to go into our output, or possibly as a pixel in a graphic, or possibly as an improvement to some sort of prediction. Or we can take that list of numbers and feed it to another classroom. This is called a multi-layered network. But again, we're simply doing very simple math operations that end up taking lists of numbers, producing lists of numbers. And we can interpret those numbers as inputs and outputs, as words, graphics, sound, any number of things. That's sort of the beauty of these systems, that simple calculations can produce truly remarkable things.
Why do you need graphical processing units, which were originally designed for video games but are now in demand for this, is because you're running this process to predict each little increment of the output. And you're going to decide how many classrooms or layers. So GPT 3.5 has 96 layers. That means before you even get the first increment of a first word, that number was run through 96 rows of fourth graders. It's by having multiple layers that you end up getting outputs that have statistical relationships that look a whole lot like the correct answers in the training data. That's what your goal is to have your model be able to put out a language output that uses language patterns in the way that the inputs were. It's really about pattern analysis. But the crazy thing, and it took me a long time, is that this is happening. These tokens in the GPT model are not even entire words. They're more like syllables. So you're doing this, boom, boom, boom. So you get a 5-page brief. Think about how much computing power you must have done when you had to run it through all these layers just to get half a word. And I've got 5 pages. So that's a lot of cycles. And you've all used these technologies. Sometimes you have to sit there and wait for a little while. Feels like a video that's buffering, but actually what's happening is there's a whole bunch of fourth graders doing a lot of math.
They're basically that thing we just showed you done a couple of different times. What it means is that these generative systems that seem to be doing more than simple classification are simply built out of classifiers. Classifiers used in very, very clever ways. So the big breakthrough with transformers was this idea called attention. The idea that you see that word bank at the end. I don't know whether that refers to a financial institution or the side of a river. In order to figure that out, I need to look at other parts of the sentence, the word boat or the word money. That tells me what the meaning of bank is. How can I figure that out? Well, the simple way is I write a classifier that says, given that I know the word bank is here and that the word money is in this position, does that tell me about what the meaning of bank is? The classifier says, yes, 95% of the time, that's going to be very, very helpful to you. Whereas if I ask about bank and the word to, it's going to say, that doesn't tell you anything. That's the attention mechanism. It's a simple classifier. Once we have that classification of which information is useful and which information is not, then we can just run it through another classifier. And that classifier can now tell us, okay, given that I know the word bank is there and the word money is there, I know what the meaning of this thing is. And that's ultimately the sort of engine that allows for all of our natural language processing systems to work if they're using the transformer architecture. It's, again, built out of classifiers, which is really remarkable. We're able to generate information simply by classifying information in clever ways.
This is now why we've got lawyers who are starting to counsel their clients, don't give this machine confidential information. It will learn the patterns in your confidential data that it can then remember for future use. The more context you give the math, the more sort of customized an output you're going to get. So there is this question about what the heck did you use? So we don't entirely know. OpenAI, when it was still a nonprofit, produced a research paper. I think other data sets have been added, but at the time, the main data set is called the Common Crawl. This is a nonprofit that basically tries to make a copy of everything it can find on the internet, and it's been doing this since 2008. That's probably the foundational text and image data set that's being used. WebText 2 is basically going back into the web and now using conversations where people are exhibiting the conversational behavior that this is trying to be modeled on a forum like Reddit, and they're linking out to a bunch of web pages. So that you're saying, well, these are the links to pages that people in conversation thought were relevant. Let's focus and give attention to those. In litigation right now is the fact that some books were also the basis of the training, and there's some opacity around which books, where did you get them? On the one hand, it might be Project Gutenberg, in which case they're all, from a copyright law perspective, they're all in the public domain. Other allegations are that some shadow library was used and that books under copyright were copied. And we'll let the lawyers who are doing discovery in these cases sort of get that cleared up. Google's Bard, what we know there is it's somewhat similar. So it's a filtered version of the Common Crawl. It's Wikipedia, it's other code, and then 50% of quote unquote dialogues data from public forums. So that's pretty open-ended. We're not sure exactly which forums or anything like that. Meta, we know even less, but again, the Common Crawl is the sort of core engine, and it's basically stuff you find on the web, but books are, again, one of the questions that are in litigation there. On the image side, Leon is another nonprofit that basically takes the image subset from the Common Crawl. And this is important because the labeled data performs better and they create image text pairs. The thing about the image generators that's interesting is it first has to use that transformer architecture to read your text prompt, figure out which parts of the text prompt are most relevant to image generation, translate that then into an image generation process. So by getting all of these image text pairs, you're basically getting more structured data that gives you better results. And now I'm going to fast forward to images, early image generation. So, okay, give me an image of Vincent van Gogh giving a TED Talk. All right. So there's some Van Gogh-ness to the image, but it's blurry, it's not very accurate. But you just keep feeding it back and say, okay, that's close, but that's not really a very good representation. Can you do it better? So after training it more, you might say, okay, here's a self-portrait. Can you make a photograph image from this? And the answer is yeah. And that's pretty convincing. So this is what a better trained image generator can do. It just keeps self-adjusting those parameters. Some basic takeaways that answer some of our copyright relevant questions. I've written a novel. You've trained your model on my novel. I'm outraged. You've copied my novel into your model and it knows all about the minor characters in my novel. Well, it might be able to create outputs, but your novel is not in the model. It just has statistical relevance. And it probably has that relevance, not so much from your novel, but about all those people on Reddit who were talking about your novel and talking about that minor character. And that may be why the output seems to know more than it does. Do remember, these are just prediction engines. They're not knowledge bases. They're not search engines. Their design is to predict, but there are problematic outputs. Sometimes it sure looks like it's just making a copy. It's not copying from in the file. And yet you can start the first lines of Harry Potter and Dumbledore, rest in peace. Charles, how is it that if I start typing it and it gives me essentially word for word Harry Potter, isn't it in the model?
So it would seem so. What the model is doing internally, though, is it's basically saying, given that I've seen these words, what is the statistically most natural word to put next? Based on all of the training that's been input, all of the grammatical constructions that have been sort of inferred, what word seems to fit there? If you've seen the opening to Harry Potter so many times, that makes that next word of the book a highly likely output. And so that means that it has basically determined that that is statistically the most reasonable thing to put there. It's simply making that sort of statistical inference.
We don't want to answer the legal questions per se, but to the extent that we want to ask whether the work of authorship has been fixed in a tangible medium in the model, might this particular work of authorship be fixed in the model?
It's hard to say. I know that there's sort of a debate over whether or not something that's sort of in the model that where we can't actually discern it based on the particular weights and biases hidden somewhere in that model, whether or not that thing is inside the model. But I think what's ultimately happening is that it's really learning a fact about the world in a sense. It's learning a fact that it turns out that when people say these words, the next word should be the thing that it's seen through the training, and that happens to be the first word of Harry Potter. It would be almost impossible to actually discern where in the model that is, I guess.
Okay. And now just shift perspective for a minute. Is this a good outcome for the model builder? No, right? The point is, if I want to make a machine that can copy Harry Potter, I don't need to spend all this money on all these machines to copy Harry Potter. Yeah. So statistically, this is called overfitting.
Yeah. In a sense, if you develop a model that simply replicates its outputs, you've kind of developed a useless model. Say that I'm trying to develop a model that predicts the weather based on how much it's raining and the humidity and the temperature, right? And I give it 10 examples. Well, one thing this model could do is say, if I see the exact temperature, humidity, and rainfall of this situation, then I know the weather is this, and I'm going to give you no answer otherwise, right? That would be a pretty useless weather predictor, right? We don't want the weather predictor to learn that. We want the weather predictor to say, humidity tends to correlate with this, temperature tends to correlate with this, there's an interaction between the two of them, and based on that, I can predict a range of weather outcomes. And that's ultimately what we want in these sorts of systems as well. If they're simply memorizing their outputs, they're not doing things that are useful. They're not going to be able to generate new things, which is ultimately what we want them to be able to do. So in a sense, the overfitting problem is something that designers and trainers of generative AI systems are really trying to avoid.
And we can fix it in different ways. One is if you don't get your statistics right, you can make a math error that will produce that result. This is more of a data error. You've got too many copies of the first chapter out on the internet. So this one you can fix. Go into the training data and deduplicate. Just have one copy and not multiple copies, and then you'll stop getting a one-for-one reproduction. There's another problem, and this is a hat tip to Matt Sag, who's been playing around with Midjourney, which he calls the Snoopy problem, which is if you're looking for image-text pairs and you give it the text Snoopy, it's going to produce something that looks a whole lot like Snoopy. Why? Because in the training data, there are multiple image text pairs where people talk about Snoopy and you get Snoopy. This one is harder. Deduplication is not really the solution. And this is going to be a challenge for the model makers to figure out. And one way to do it might be to have to slap on some lawyer rules on top of the model. This is one of my predictions, is that we're going to start to see content moderation have to be layered on top of the outputs to deal with specific kinds of problematic outputs. And this would include other kinds of problematic outputs, not just copyright infringing outputs. The other issue is the style issue, and this is going to come up in our infringement panel. It can learn an illustrator's style. So Greg Rutkowski is a very popular Oregon-based illustrator. He's fond of dragons. And so there's lots of dragons on the internet, and you can ask for dragons and you're going to get dragons. So why? Is this just the Harry Potter problem in image?
You want to be able to think about this in terms of statistical correlations. It turns out that when people ask for dragon pictures, this is a pretty common way of drawing dragon pictures, actually by a lot of people, honestly.
Well, and I should be clear that these people don't want dragon pictures. They ask for it with Greg Rutkowski's name in the prompt.
And again, so what the system is going to basically be doing is it's going to say, well, I've seen a lot of labeled images that look like this when I put the author's name in there. And so that means there must be a correlation between those two. And so when you ask it to produce another image in that style, it will say, of course, I can do that because I know the correlation between the name and the type of graphic. It'll produce a different graphic almost all the time, but it will sort of infer essentially the sort of characteristics, the luminous background, the shadow nature of the dragon, the spikes on it. Those sorts of features, it'll determine because they are statistically correlated in the training data with this name.
I'm going to fast forward. The transformer is not actually that much more complicated. It looks like that. This is the only other cool thing I learned about the image generation is instead of saying predict, is this a real image or fake? What you do is you feed the model a real image. You add a bunch of what is called statistical noise, which basically blurs the picture until you get to a point where you're only giving the picture a bunch of white noise. And you're asking it to predict what this initial image was. And the only information you're giving it is, this is the blurry image, and this is the schedule by which I added noise at each step. And you basically have to then reverse engineer that, starting with the noise and predicting which parts of each incremental step was noise, subtract it out. And if you do that, you should be able to produce basically something that looks a whole lot like the original image. So that's the training process. By training that, it knows what counts as noise and what counts as image. And that's how you end up getting dragons in the style of Greg Rutkowski.
I think the important thing about that, though, is it's all classifiers, right? We're just building a classifier that says, starting from blurry image, make sharp image. And then by repeating that process over and over again, we manage to get a very nice sharp image.
All right. So here are the technical questions that the Copyright Office asks. I first want you to answer in your head, and then I'm going to ask Charles to give us the real answer. Again, this is not an ex parte submission, but it would be useful for the rest of the day if we had an answer to these questions. Let's not answer the legal question.
Well, so this goes back to that picture that I had where we had the pictures of the cats on one side and we had yeses and nos and check marks on the other side. We're using these to run through a numerical system to figure out how good that numerical system is doing. We then are updating that numerical system. But again, no single number in there is intended to be tied to a specific image. We're always trying to figure out things about the class of images, about the whole set. We're trying to derive trends and overall patterns. So in that sense, they're used to inform, but they're not used as the basis for anything. Again, this is not the Cookie Monster model of ingestion where we're taking one image and saying, nom, 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 I understand it now. We're looking at the whole set as an aggregate to find patterns, to find statistical correlations.
One analogy that Charles was presented with is it's sort of like the process of baking. If each input is just an ingredient.
Yeah, so if you bake a cake, you start off with eggs, flour, sugar, and such. Your first step is you mix them into a batter that now looks nothing like any of the original ingredients. You then bake the thing into a cake that looks nothing like the batter, and then you ice the cake into something that looks nothing like the baked cake. And so in each of these steps, there's a relationship between the inputs and the outputs. But you don't see bits of egg in the final product. And so that's really what's happening. We're basically using these layers of computation to try to build inferences, to try to derive correlations, but not simply to replicate the outputs. It would be a very strange system if we do that.
Now, I think this question is very telling and interesting because of the use of the word inference and what we as lawyers think of the meaning of the word and the fact that it has a meaning in statistics as well. So take a minute and think about what you've learned. How would you interpret this question and answer it if we were using legal inferences?
Yeah. So, when I write a brief, right, if I'm being asked to infer something about the case law in order to determine an outcome, I cite cases. I infer, this is the rule against perpetuity, CEG, case 1, case 2, case 3. So I have a well-defined set of sources that informs my input. That's what we do in legal reasoning. And that's going to be very different from what we do in machine learning.
So if we were to say, you've actually used an ambiguous word in your question, it could mean legal, it could be to the extent that you're asking about, can the model infer from specific sources other than, we have to put an asterisk on this, right? Other than the Harry Potter problem, the general answer is no. If, on the other hand, you mean statistical inference, then how do we answer?
Statistical inference is going to be closer to like one of those old English treatises where the author says, I just read all the cases and this is what I think the rule is. And they can't really express where it came from because it's just based on having ingested a whole bunch of case law. Same thing with like a statistical correlation. If I do a linear regression, I end up with two numbers that define a line that tell me all sorts of things about the data. It's not attributable to any single piece of input there. It's the result of understanding a pattern out of the whole thing. And that's really what the sort of inference that we're talking about in machine learning or statistics is all about.
Okay, how about this?
So number one, this is an active area of computer science research. A lot of people are trying to figure out how to solve the unlearning problem because of the right to be forgotten in Europe and such. But if you think about it, this is basically the problem of trying to take the eggs out of a cake, right? It's all mixed in there, and I'm not going to be able to find the little bits, right? Because they have been so well incorporated into everything else. In the same way, the model incorporates all of this information in ways that we don't fully understand in a lot of situations, such that trying to extract a single piece out of it is at best a very, very difficult task. And that's why basically the question says, in addition to retraining a model, because that's the sort of industry standard for how you do it. If you want to take something out, you just redo the process with that record taken out of the input.
Just to be clear, it does seem like the premise of the first sentence is just mistaken, right? It thinks that the statistical correlations are based on a single piece of data. And as Charles just explained, that is not what's going on in the model, other than the Harry Potter situation. So it's possible, but that's a mistake from the model design. If that's what's happening, the model's not working the way it's designed.
And even with the Harry Potter situation, it's not like we're going to be able to go in there and see, that's the fourth grader who cares about Harry Potter. We're not going to know where that is, right? That's going to be mixed into a lot of other things. And so even where we can see just direct relationships between the input and output, all those fourth graders are doing things that we can't quite figure out, at least with our sort of ordinary capacity and ordinary research tools. And we're not going to be able to take it out unless you're just sort of adding a filter at the end that says, stop putting out Harry Potter, or we retrain the model entirely.
So that's, you got two choices, retrain or put a filter on the back end. But there's no going in and sort of artisanally plucking data out of the model. How about this one? No. Right? No way.
And particularly, that thing I showed you where I said you start with all the training data and you make all the answers and you evaluate that. Often that is computationally infeasible. That is just too much work. And so you just take a random sample of your input data, this stochastic sampling. And what that means is that because we're just taking random samples, we don't even know which training data went into the thing in a lot of cases. So there are situations in which you can have genuinely no idea what the actual training data that fed into a model was.
All right, we're going to stop here. And I want to just thank Charles for, it's been really exciting and hard to learn the facts.